All right, this is CS50, and this week we begin to introduce web programming. That is still writing code ultimately, but whereby the user interface is now going to be a browser or even a mobile device ultimately. To do that, we're going to introduce you to first some fundamentals of how the internet works itself. Then we'll transition to a language, but not technically a programming language, called HTML, Hypertext Markup Language, followed by another language, though also not a programming language quite yet, called Cascading Style Sheets, and ultimately we'll reintroduce some proper programming so as to automate much of what we'll be now discussing. But first, let's begin with what underlies the World Wide Web, or web for short, which is the internet itself. And it's perhaps simplest to think of the internet as like the underlying plumbing that allows us to get data from point A to point B. So there's lots of computers in the world nowadays. They are all physically connected somehow or virtually connected with wires or wirelessly. And if you can imagine each of those computers somehow being able to talk to one another, that then is our internet, an internetworked set of computers that can somehow intercommunicate. But it wasn't always that way, even though you and I take for granted the fact that we can all talk electronically nowadays online. Indeed, early on, there were only a few points of presence on this here internet. So for instance, here is the United States in 1969 when ARPANET, which was developing what we now know as the internet. And there were only a few locations here, primarily on the West Coast. And those universities initially were indeed able to intercommunicate, sending the first emails, for instance, even before there was a World Wide Web. Eventually, some other universities came online, Harvard, for instance, among them on the East Coast of the United States, and then East Coast and West Coast were suddenly able to intercommunicate as well, as with emails and the like. But in order to get data from point A to point B, so to speak, in this case, West Coast to East Coast, not to mention the rest of the world, once more and more servers were introduced to this mix, we needed to somehow route the information. And so one of our first terms of art today will be that of routers. Routers are simply computers, or technically servers, whose purpose in life is to route information from one point to another. Now, these servers might look a little different from your laptops and phones, certainly. They might look different from your desktop PCs, but they're still just PCs. Computers that maybe have a different form factor, a different shape, but that typically live in what are called data centers, like big warehouses that store lots and lots of computers. Those computers have lots of cables that interconnect them with other computers there, as well as other warehouses and data centers, much like the dots you just saw on the screen. But the software that those servers are running give them the ability to route information from one location to another. So if I here am representing the server, essentially these devices need to decide when they receive some information, an email, a web page, or the like, does it go this way or this way or this way or this other way? And they use software to figure all of that out. Now here we have a visualization in the spirit of using Zoom from some of our former teaching fellows who acted this out. So if you can imagine a teaching fellow named Phyllis wanting to send, say, an email to a teaching fellow whom you might know, in fact, named Brian, well, Phyllis might put that message in some kind of envelope. Here physical, but think of it as virtual as well. And she's going to hand that envelope off to the next router near her. And maybe it's above, below, to the left or the right. But generally, this envelope is going to take some path from point A, Phyllis, to point B, no pun intended, Brian. Let's take a look. Wonderful. So many thanks to CS50's team for making that visualization possible and how well it worked, getting the data up, down, left, right from Phyllis to Brian ultimately. But how were those teaching fellows, how were those routers making decisions? Well, in this case, we actually practiced quite a bit, but in the real world, it's all dynamically figured out via software in some form. And the language that routers typically talk in order to figure out how to get from point A to point B is a language, or really a protocol called TCP/IP, which is technically two protocols together that each do a little something different. And in fact, let's focus on the one that's probably generally familiar to many of you, namely IP. So even if you're not a computer person, odds are at some point you've heard of IP, perhaps in the context of an IP address. IP stands for Internet Protocol, and you can think of this as a language or a protocol, to be more proper, that computers speak when trying to send information between each other. And a protocol is really just a set of conventions conventions. And so, for instance, in the human world, much of it, if I were to extend my hand to you upon greeting you for the first time, most likely, depending on where you're from, you would know instinctively to reach out with your hand and shake my hand, completing a human protocol. So it's not so much a language that we're speaking, but a set of conventions. And indeed, that's what TCP and IP are. But IP is very specifically focused on addressing servers in the world. So what do I mean by that? Well, it turns out that every computer in the world that's connected to the internet has what's called indeed an IP address, a unique identifier that typically is of this format: something dot something dot something dot something, where each of those somethings is a number, a simple integer. Those integers are typically 0 through 255, which is to say that you have 4 values in a typical IP address that's between 0 and 255. If you're doing some mental math now, you might recognize those numbers. Anytime you're counting from 0 to 255, you're using 8 bits or 1 byte, which is to say that an IP address, as represented here with these hash symbols, is 32 bits in total, or 4 bytes. So your mind can immediately start to wander, if you do some of that mental math, to conclude that, oh, it would seem that you can have no more than, per past discussions, 4 billion IP addresses, because 2 to the 32nd power gives us 4 billion, especially if we don't have to worry about negative numbers, which is to imply that there can only be 4 billion devices on the internet in total. Now that's a lot, but there's also a lot of humans in the world, and there's a lot of humans with multiple devices, laptops, desktops, not to mention all of those servers and Internet of Things devices. So the world not only uses this format nowadays, which is technically called IP version 4, there's also a new and improved version of IP addresses known as IP version 6, which the world is starting to use, especially some of the bigger companies and internet service providers out there. But odds are your computer and my computer still tend to use IPv4, this format. So we'll focus on this one, if only because you're likely to see it in the near term in the real world as such. So how does this all work? Well, this is perhaps the most cryptic looking diagram I could find that represents exactly how IP works. Now, this is sort of ASCII art, and this is actually a diagram from the specification, or RFC, request for comments, that defines how IP, the Internet Protocol, is supposed to work. And what this diagram is implying is that anytime you want to send a message over the Internet using this protocol called IP, you first have to make sure that you write an address on the envelope, and you write another address on the envelope that is your sender address or source address. And the way you do this, of course, is not something physical in an envelope, but rather you use a sequence of bits that indicates what the source IP address should be and what the destination IP address should be. And then let me wave my hand. There's a whole bunch of other bits being used anytime you send information on the internet, in addition to that source address and destination address. So this, though, is essentially written on the outside of this envelope in this here way. Now, what does that really mean? Well, let me make this a little more concrete. And just for the sake of discussion, suppose that Phyllis, in our example, was sending indeed an envelope virtually to Brian from point A to point B. Then let's suppose, for the sake of discussion, that Brian's IP address is a number like 1.2.3.4. So metaphorically, what Phyllis would do, or really Phyllis's computer would do, is write that IP address right in the middle of the envelope, just like a human would when addressing a letter in the real world. But so that Brian could potentially reply to her, either with new information or at least to acknowledge receipt of this same envelope, she's also going to put her IP address in the top left corner, and maybe her IP address is 5.6.7.8. Suffice it to say, I'm making up these numbers to keep them simple, but they could be actual IP addresses because they fall into that format of something.something.something. And so now when Phyllis hands this envelope off to the person or the router next to them, next to her, that router can look at the same envelope, realize, oh, this is going to address 1.2.3.4. I might not be physically next to Brian, that IP address, but I can at least hand it off to some other router that might be closer to Brian and therefore know how to get it to him eventually. And so what routing is all about is exactly that. These servers passing off, metaphorically, these envelopes back and forth, ideally getting them closer to their destination. Now, unlike the real world, where the shortest distance between 2 points is a straight line, you might recall that Phyllis didn't actually hand that envelope up and to the right diagonally to Brian. Rather, it went up and down, and it didn't necessarily follow the shortest path. But in the real world, routers might at least ideally route data in the fastest way possible. So even though they might traverse geographically disparate routes, sometimes because the servers are faster or less busy, it might make more sense to spend a little more distance to get the data there based on how the servers are configured. And also finances might be involved. There's a lot of big internet service providers in the world, the Comcast, the Verizons of the world in the United States, for instance. They might have relationships with other internet service providers such that they want to ideally keep data on their network so as to not have to pay fees to route the data on someone else's network, so to speak. So there's lots of ingredients that go into deciding how to get the data from point A to point B. But in general, it doesn't really take more than 30 hops, so to speak, 30 passings of the envelope from router to router, because at that point, it's probably stuck in a loop if it's going on for more than, say, 30 such hops. So what's really written on the envelope is more arcane information like this, but it's just patterns of bits. So it's as though Phyllis was just writing patterns of zeros and ones on this envelope that adhere to this pattern, and then inside of the envelope is what Phyllis might actually want to send Brian. Now, what might that be? Well, as you know, the internet is filled with cats. And for instance, here is one such picture of a very happy cat. Unfortunately, it's a pretty big picture. And if you can imagine this being maybe a video instead, it would be even bigger in terms of its file size, even more bytes. And so what computers typically do is they additionally fragment information when they're sending it on the internet. So rather than try to shove this big cat inside of that envelope, what a computer would do, even though this feels a little sacrilegious, would be to tear happy cat in two, maybe even into 4 parts, and then put each of these fragments inside of an envelope, followed by another fragment inside of another envelope, at which point, to be fair, Phyllis had better address the second envelope as well, probably with the same amount of information. So she would probably put 1.2.3.4 on the middle of the envelope, and 5.6.7.8 in the top of the envelope to indicate that this one, too, is destined for Brian's IP address as well. Unfortunately, once we start chopping things up into fragments like this, it's no longer sufficient for the outside of the envelope to indicate only the destination. Because what if they arrive in this order, or maybe this order, or some other order altogether? After all, there's nothing stopping Phyllis from handing one envelope here and another envelope here, so long as they eventually make their way to Brian. So he's going to need a little more information in order to reassemble this data at its destination and know ultimately just how many total envelopes were sent to him. So how can we go about doing that? Well, let me propose that we introduce another protocol as well that will help us guarantee delivery of this information. So there's this other protocol, TCP/IP, and it's typically written or said in the same breath as IP, such that we talk about TCP/IP, but it's a separate protocol. And TCP's purpose in life is to solve a few problems. For instance, among the problems that TCP does for us is it ensures that we acknowledge exactly how many envelopes were sent. So for instance, on the outside of this envelope, we might write not only the destination and the source address, but I'm also going to say something like 1 of 4 in the memo field of the envelope. We don't often use this in the real world, but if you were to, you could put it down there. And then in the other envelope, I might write 2 of 4. And so that now Brian, upon receipt of that, can see that, oh, this is the second such envelope. And I could keep doing this for number 3 and number 4. And what this allows Brian to do ultimately is not only confirm that, OK, I got pieces 1 and 2 and 3 and 4, he can also infer if he's missing any pieces, lest he have a very unhappy cat that's missing an entire quadrant of that there picture. So TCP accordingly can help Phyllis guarantee delivery by establishing an additional protocol on these virtual envelopes that dictates that we also keep track of the sequence numbers of these here envelopes so that Brian can infer if anything has been missed. Otherwise, he can acknowledge, thank you, Phyllis, I got all 4 of these. But there's another problem that TCP solves for us, which is that the internet itself does so many different things nowadays. We've got email. We've got the World Wide Web. More on that soon. We've got video conferencing. We've got streaming media and so many other applications that run on top of the physical infrastructure that is the internet. So what else does TCP do? It also defines a convention for what we're going to call ports. A port is simply a unique numeric identifier for a specific internet service. And years ago, a bunch of humans decided to standardize what these port numbers are. So for instance, a bunch of humans in a room decided that, you know what, to uniquely identify World Wide Web traffic, let's use port 80. So the number, the integer 80. But if it's securely sent using not HTTP, but HTTPS, more on those also a bit later, then it's going to use port 443. And there's other numbers as well. 25, for instance, is commonly used for email. 53 is commonly used for DNS. And there's other integers as well, a much longer list than the two here on the screen. What Phyllis can then do is if she specifically wants to request a web page of Brian, whereby Brian is now not only the recipient, but a web server that has pages of content, what Phyllis can do on the outside of this envelope is add essentially a colon and then a port number, such that now the destination is still 1.2.3.4 colon 80. And this indicates that when Brian receives this envelope, he, as a server, knows that this envelope is destined for not the email server, not the video conferencing server, not the streaming media server, but rather for the web server that happens to be running at Brian's location. And in fact, this is because, as an aside, when we talk about a server, singular, can actually do multiple things. A single server can handle email and web and video conferencing and more. And so what these port numbers ultimately allow servers to do is to multiplex, so to speak, or distinguish which server or which type of service should be handling this inbound request, so that Brian replies with a web page and not, for instance, an email or something that's inappropriate like that. Meanwhile, if we want to get our hands a little dirtier with the underlying format of these things, even though I wrote it on the outside of the envelope as just colon 80, what's really happening underneath the hood is a little something more complicated like this, whereby Phyllis would write not only a destination port, but also a source port. So it turns out even Phyllis uses a unique identifier so that Brian knows how to address his response to her specifically. And there's that sequence number and the acknowledgement number that I alluded to earlier, whereby TCP ensures that we can keep track of 1 of 4, 2 of 4, 3 of 4, 4 of 4. So long story short, what TCP IP together allow us to do is uniquely address computers on the internet, as by using IP addresses in a standard way, and to guarantee delivery of data between 2 points by using these sequence numbers and as well as these port numbers to make sure that the data gets where it needs to go. Now, I'm using guarantee a little bit generously. If the internet goes down, the power goes out, TCP is not going to get data from point A to point B, but assuming the internet itself is working, that is what these protocols together do. But to recap then, with TCP IP, we have this mechanism for addressing computers uniquely, much like we do already in the real world. And in fact, Sanders Theater, for instance, is 45 Quincy Street, Cambridge, Massachusetts, 02138 USA. That is exactly what you could write on the outside of an envelope to mail it physically to Sanders Theater. What we're talking about then with these virtual envelopes is exactly the same idea, but in a way that supports servers sending the same data, and it turns out that just dealing with numbers like IP addresses is much easier than full text like things on the outside of our own envelopes. Indeed, imagine how much happier the mail service, the postal workers would be if all we were writing were very clean numbers on the outside of the envelopes, and they wouldn't have to read messy handwriting with much more complicated strings of text. All right, so it stands to reason then that this seems to work, at least as I've told it here. But of course, none of us probably use IP addresses explicitly every day. In fact, when you go to a website, you probably type google.com or cs50.ai or other such domain names. And yet, here I am telling this story that underneath the hood, a la Phyllis communicating with Brian, everything uses IP addresses, not to mention port numbers and sequence numbers on the outside of these envelopes. Well, suffice it to say, your Mac, your PC, your phone is somehow figuring out how to write those numbers on the envelope, even though you and I as the humans are only typing in actual domain names like google.com, cs50.ai, and the like. So how does that all work? Well, in the world of the internet, there's other types of servers out there as well. Not just routers that route data from point A to point B. There's also DNS servers as well, domain name system servers. And these typically live inside of your internet service provider's network, or on your university's campus, or in your company's office, or somewhere in between you and the rest in the world. And what a DNS server does, in short, is translate domain names to IP addresses so that you and I, as humans, can type the more user-friendly version of google.com and cs50.ai, and you and I don't have to worry about or figure out what the underlying IP addresses are. Now, it turns out the implementation of a DNS server follows a familiar paradigm. We've long talked about dictionaries now, an abstract data type that allows us to associate keys with values. Well, in the case of a DNS server, they essentially have inside of their memory a 2-column sheet or table, the first of which is the domain name, the second of which is an IP address. Technically, those domain names are called fully qualified domain names because it might be something like google.com or www.google.com or some other subdomain therein. So what it is you type would be in the left-hand column here, and what it is that gets written on the envelope would be in the right-hand column here instead. So now this table, you could imagine it being very, very big. I mean, there's thousands, hundreds of thousands, millions of domain names out there nowadays, and surely your phone in your pocket doesn't know about all of them, but that's okay, because the design of DNS is actually to be very hierarchical, so that your internet service provider probably has its own DNS server that can translate many domain names to IP addresses, especially if they're popular ones, and therefore they have looked up the IP address already in the past for their customers. But if you visit a random website that's not very popular and no one has visited at all or recently, your internet service provider can recursively ask another DNS server for the answer to the question, what is the IP address of that domain name? And in fact, around the world, there are what are called root servers. A small number of servers that, for instance, know about all of the .coms and all of the .orgs and all of the .govs, and similarly for other countries as well, whereby those servers, even if they don't know the exact IP address, they might know the IP address of another DNS server who does have the answer. And so long story short, if you've ever bought or really rented your own domain name before, or if that's something you choose to do in the future, essentially what you're doing when you pay someone some number of dollars per year to buy a domain name is you're asking them to add an entry to their DNS server or someone's DNS server that associates that domain name henceforth with a specific IP address of your server or server. So someone somewhere is doing that for you. But the whole process is indeed recursive, because if your ISP doesn't know the answer, it can maybe ask another DNS server, or maybe these root DNS servers as well. Your own Mac, your PC, your phone might itself cache or remember these answers though too, because it's a little silly in terms of design if your phone or your laptop or desktop has to constantly ask that same question every time you visit google.com. Odds are the IP address is not going to change, or at least it's not going to change that frequently. However, again, if you've ever set up your own domain name, if you've ever moved it around or something has changed about it, sometimes you can break a website by changing its IP address, because there's lots of servers in the world that have cached, C-A-C-H-E-D, or remembered the old IP address. But thankfully, the other feature that DNS provides is expiration dates. So essentially, the answer to the question, what is the IP address for this domain name, typically expires after a few seconds, a few minutes, a few hours, a few days. Unless you really mess things up and say, don't expire this for a year, then your website could in fact be a dead end somehow. So this is worth knowing for future web developers doing things in the real world. So DNS, to recap then, simply converts domain names to IP addresses, and technically it can go in the other direction as well. And so when you, as a human, go to a browser on a laptop, desktop, or phone and type in google.com, enter, or cs50.ai, enter, what essentially happens is your device checks its local cache to see if it's already been asked that question before. And if it has, it just immediately knows the IP address, writes it on the outside of the envelope, so to speak, and sends out your data. If it doesn't know the answer, your computer is going to ask the local DNS server, which might ask another DNS server, which might ask another DNS server, but recursively, you will eventually get your answer if that domain name actually exists. And at that point, your computer can indeed write the correct IP address on the outside of the envelope, add any sequence numbers, add any port numbers, and voila, it's on its way from point A to point B. So that then is DNS. How about one other acronym that's a bit related here too, that of DHCP. And let me assure that it's not really that important to memorize like what all of these acronyms stand for, but rather it is useful, I think, to generally know what they in fact do. So DHCP is Dynamic Host Configuration Protocol. So there we have it, another protocol, a set of conventions. And the purpose of DHCP is to actually give your computer an IP address when it boots up. This wasn't always the case. Back in the day, if you've had internet connectivity for a while, some technician probably would come to your house when you or your family signed up for internet service. They would probably have a sheet of paper on which was your personal IP address. And if you wanted to connect your PC to the internet, they would type that IP address manually into your computer so that your computer knows what IP address to use when talking to other servers. That's not particularly scalable. That's not particularly maintainable. You don't want the technician to have to come out just to make a change or something like that. And you probably want to be able to use multiple devices as well. And so nowadays, what most computers use is DHCP to dynamically figure out what is their IP address. And so nowadays, when you first open your laptop in the morning or boot up your PC or take out your phone, if you haven't used it in a while, and therefore it no longer has an IP address because these two expire after some amount of time, your phone, your device will broadcast a message like, "What is my IP address?" And hopefully, on the nearby network, in your home, in your company, at your university, or in your internet service provider more generally, you will hear an answer, "Oh, use the IP address 5.6.7.8. For instance, in the case of Phyllis, or 1.2.3.4 in the case of Brian's recipient address as well. So the people who run these servers, the internet service providers of the world, the system administrators at your company or campus, they can come up with the rules via which these IP addresses are assigned or who gets what number. But ultimately, DHCP is just another protocol that governs how your device gets its IP address. But that's not quite everything. It's actually kind of neat. DHCP servers also tell your computer what DNS server to use. They give you the IP address of one or more DNS servers to ask questions of. DHCP servers also tell you the IP address of your default gateway, the router that you should use by default to hand one of those envelopes to. And this is indeed why Phyllis probably knew to whom to hand that envelope in the first place, because when she booted up, so to speak, she was assigned an IP address, she was told what default gateway to use, and the default gateway, aka router, these are just synonyms, is the device to which she should hand off data by default in order to get it from point A to point B. So why do we focus on all of these acronyms, all of these technologies? Well, on the one hand, they're sort of omnipresent. And even though you might not need to say these acronyms verbally all that often, you're going to see them on occasion. When something goes wrong, you're going to need to troubleshoot things like this. But more importantly, they're sort of representative of very real-world engineering problems that the world has had and encountered over the years. But they're relatively simple solutions there, too. I don't necessarily know how I could write code to implement a DNS server or DHCP server, and perhaps neither you, but it sounds like a pretty simple idea. If I have the ability in code to hear requests, I can respond to those requests by maybe using a dictionary in memory, and in the case of a DNS server, and responding to those answers. So this is to say all of the fundamentals, all of the ideas we've been talking about throughout CS50 really are used as building blocks to solve these very real world, very omnipresent technologies that you and I now take for granted every day. Let's now consider one other protocol that's with us every day nowadays, that of HTTP, Hypertext Transfer Protocol, which is indeed itself a protocol, a set of conventions that governs, in this case, how web browsers and web servers intercommunicate. It is very much related to HTTPS, which is literally the secure version thereof, that somehow uses encryption, somehow scrambles the data to ensure that when you're visiting a web page, you and only you can see that web page, and no one in between you on the internet actually knows what it is you're looking at or the specific URL that you are visiting beyond the name or the IP address of the website itself. So even though you and I probably don't even bother typing http:// or https://, odds are nowadays you and I just type google.com, enter, cs50.ai, enter, or you click on a bookmark. Underneath the hood, this protocol is everywhere, and those prefixes, http and https:// are required when using a browser, even though your browser automatically tends to insert those prefixes automatically if you, the human, don't bother typing them yourself. So they're used, of course, in URLs, Uniform Resource Locators, which specifically are the addresses that we use to get to useful information on the World Wide Web, or web for short. Here, for instance, is one of the simplest URLs we can talk about. I'm going to use HTTPS deliberately to imply that you really do want to try to use secure sites alone nowadays. But this domain name would seem to be www.example.com, or that's the fully qualified domain name itself. But let's tease apart what's going on here. Typically, in your browser, you might see a trailing slash, so a / at the end of it, which just indicates, albeit non-obviously, that you want the default web page at that domain name. In particular, you want to be able to access whatever the default content is for that website. Nowadays, though, browsers like Safari and Chrome and even others tend to hide these details just to simplify what you're actually seeing in your browser. But typically, if you click or double-click on the URL bar in your own browser, you'll see more information, including this trailing slash. So if you only type in google.com, enter, probably your browser is automatically appending the / to indicate you want the default home page. But sometimes there's more to the URL. Sometimes it's /path, where by path I just mean a folder or a file name or something along those lines. And that's more specifically referring to like probably a directory on the server containing some web page specifically. Sometimes it's more explicit. Sometimes the URL might literally end in .html, which is going to stand for hypertext markup language, one of the first languages we'll soon look at in detail. And that's the language in which web pages are written. So what this URL indicates is that at the server called www.example.com, there is a file called file.html that this user wants to see in their browser. Sometimes, though, and it's not often the case anymore that you see these file extensions. The world decided years ago that these are just kind of ugly and not strictly necessary technically. So sometimes you'll just see /folder/, which just means there's a folder, aka directory, somewhere on the server whose web page contents you want to see. Sometimes it's nested. Sometimes it's a folder and then a file inside of which is the web page contents that you want to see. So in short, URLs generally follow this kind of format. And there might be 0 or more of these folders and maybe a file name explicitly or not. But what else is going on here? Well, here we have the fully qualified domain name. And just to toss out a bit more jargon, technically when you say domain name, typically you mean something like this, just the example.com. Because the www in this context is generally referred to as a host name. It's like the name of a specific server at a company, at a university that is providing some service like this, the World Wide Web, aka a web server. It is not strictly necessary for a server to have a name of www just to be a web server. For many years, MIT's website was web.mit.edu, whereas everyone else in the world was using www. But odds are many of you are probably not even in the habit of typing www.something.something. Rather, you type in google.com and hit enter, and the browser somehow automatically brings you to www.google.com. So the host name is the name of a specific server. The domain name is typically just something like theexample.com. And let me disclaim that's a bit of a white lie, because if you're Google, if you're Meta, if you're any of these big companies, you don't just have one web server. So technically, the www refers to a collection of servers. Maybe it's 2, maybe it's 20, maybe it's 20,000 servers. There are technologies that allow you to support that as well. But lastly, there's one other piece of jargon that's worth knowing. The last part of these fully qualified domain names is known as the TLD, or top level domain. And that is what generally, historically indicated what type of domain it is. In the US, .com means commercial, .gov means government, .org means organization. However, there are so many more top-level domains nowadays, and in fact, they're not US-centric. And in fact, just because you have .com does not mean you are in the US. It just means that you paid someone to use their domain name. In fact, there's other TLDs too. Every country has its own .us for the United States, .uk for the UK, .jp for Japan, and so forth. Anytime the TLD is just 2 characters, that's a country code. And yet that's kind of curious because we're in the habit of using CS50.ai. There are websites that use .tv. There are websites that use .io, CS50 included, and if you'd like to go down that rabbit hole, feel free to Google top-level domain, or TLD, and any of those, and you'll actually see that even though we are using CS50.ai to imply artificial intelligence, .ai has nothing to do with artificial intelligence, except that that is how you can abbreviate it in English as an acronym. It actually is a 2-character country code. And that country and others have decided to actually monetize the TLD by selling it to really anyone who's willing to pay per year to use their TLD. So lastly, within these here URLs, we, of course, have the actual HTTP or HTTPS, and that dictates the protocol that is going to be used when a web browser requests a web page at their address. Now, what does this protocol do? It's similar in spirit, again, to sort of a handshake, whereby a web browser, when it wants a web page, it's kind of like extending a hand, hoping that the web server will respond and know what to do. Of course, there's no such handshake physically here, but rather, metaphorically, the web server should know how to respond so long as the web browser standardizes the message that it sends. So what do I mean by that? Well, let me propose that inside of this envelope can be one of two messages. And this is a bit of a simplification, but the first of those messages is get. And what get means is literally get me a specific web page. By contrast, you can use post inside of these envelopes, and post generally means to send information somewhere else. And this too is an oversimplification, but generally the word get is used by a browser when it just wants to get information. The word post is used when it wants to send information, often sensitive information like a credit card, an email address, a password, or anytime you're sort of filling out a form, it's generally sent via the post keyword instead. And these are indeed verbs, like get and post are both verbs in English, implying that this is some here action. Now, ... means that there's other verbs that can be used inside of these envelopes as well, but let's be more specific. Inside of the envelope that's being sent from browser to server is more specifically a message like this. So if I, with my browser, visit www.harvard.edu, the message that goes inside of that virtual envelope, as we discussed earlier, is literally text that looks quite like this. So the cat is gone. There's no more pictures of cats just yet if you're just requesting Harvard's own homepage. But inside of that envelope is indeed get/http/to, for instance, then host, then the actual host name or fully qualified domain name that you are seeking. And ... There's some other stuff there, but that's what's inside of that envelope. Hopefully, what's going to come back from the server is another envelope inside of which is a response. So whereas the first message is a request to get something, the response is indeed a response that hopefully contains the actual web page that you requested. And you'll see that the response might look like http/to, 200, and then content type text HTML, which just means that the web page is written indeed in this language we're about to spend time with today, HTML, below which is the actual content. So how can I actually go about seeing some of this? Well, let me actually go over to VS Code. And up until now, we've been using VS Code for the purposes of writing code. But we do have this terminal window. And the terminal window gives me access to an underlying operating system. That operating system, recall, is called Linux. And I have a command line interface here. And up until now, I've been using this command line interface for commands like cd and ls, make, debug 50, Python, SQLite 3, and the like. But there's other commands that typically come on a system, including this one, that allows me to make internet requests as well. Not even with a browser, but textually. Moreover, there's always been, even though I generally hide it during class, a second tab, namely ports. And if you yourself look at cs50.dev after logging in, odds are you will see a ports tab, among others. And what you'll see here is that all this time, CS50's own development environment has been using by default a TCP port number, namely 1337, which is a very elite number for us to use. And that is the port number that's used by CS50's customizations of VS Code. Our so-called extension uses that TCP port number so that when our extension is talking to VS Code, it uses a standard port number on the outside of its own virtual envelopes, if you will. You as users don't need to care about that, but that's why that tab, all this time, if you've seen it, has had numbers in there. And soon we're going to see some additional numbers as well. But if I go back to my terminal window here, I, of course, could type commands. And one of the commands I could type is actually this. Let me increase the size of my terminal window. Let me go ahead and type curl, which means connect URL, -I. And now let me go ahead and type in https://www.harvard.edu/. So I'm going to manually type this into my terminal window's command line interface and see what comes back. I'm going to hit enter. And I get a bunch of stuff back. That's why I used a ... on my slide a moment ago. But in this output is some familiar text now. One, we saw this line earlier on my slide, http/to, and then some number 200. And then there are other lines here that I waved my hands at earlier because they weren't strictly necessary, including the host line. If this server is only doing one thing, we don't even need to clarify that this is www. harvard.edu. But what then is this HTTP/2 and this 200? Well, it turns out that the 2 is just the version of HTTP that my browser or my keystrokes were using a moment ago. 1.1 is a common version number, 2 is a common number, 3 is catching on over time, but this just indicates what version of the protocol the browser and server are speaking, even though this browser has no graphical user interface. It's just a command simulating a HTTP request to get back these headers. And that's in fact what -I means. Show me just the headers. I don't want to see any cats or Harvard news. I just want to see the headers inside of the envelope. But it turns out all this time, for as many years as you've been using a browser, you could actually do this in your own browser as well. Let me open up another tab here, and let me manually go to https://www.harvard.edu/enter. And what I'll see here is Harvard's homepage as of right now today. It all worked as you might expect, but it turns out all this time you've had access to some powerful tools underneath the hood. Let me actually right-click anywhere on this web page and select Inspect. And that's going to open what are called developer tools in the context of my browser, which is Chrome. Most every browser nowadays, Safari, Edge, and others have similar looking tools, though you might have to access them via different menus. And in fact, in Chrome, you can also go up to the ... menu and find your way to developer tools. But there's a lot going on here. But what I'm going to do is go to the network tab here for a moment. And I'm going to zoom in just for the sake of legibility. And notice here that when I clear this network tab, this is giving me access essentially to a log of everything you're about to see on the screen. And notice it just undeleted itself. Apparently, Harvard is doing something behind the scenes every few seconds, which is why that row reappeared, because indeed, I'm trying to record my network activity. But let's go ahead and do this. Let me clear that one more time and reload the page, and so many rows just flashed across the screen. In fact, in the bottom left-hand corner, you'll see that my browser, unbeknownst to me, made not one, but 67 HTTP requests. That's how many envelopes essentially went back and forth between my browser and harvard.edu a moment ago. Here comes another, and if we just keep this open, it's going to come again and again. Harvard is kind of keeping the page alive. But let me zoom out and scroll back to the very top of this and focus on just the first page I requested, and click on www.harvard.edu, and let me click on headers here. What I'm seeing is diagnostic information, if you will, about what I just did. And you'll see that the URL I requested was indeed this thing here. I used a request method of get. Unbeknownst to me, get is what is used by default when you just type a URL and hit enter. Then the status code that came back, there's that 200. So it turns out that what web servers and browsers have done over the years, thanks to HTTP, is they have standardized what these numeric codes are to indicate success or failure. In the world of programs that you and I have been writing, we typically use 0 to indicate success and maybe 1 or 2 or some other integer to indicate failure. In the context of the web, it's kind of the same idea, but the web uses 200 to indicate success and other numbers to indicate failure or something else happening as well. Well, what else can those status codes represent? Well, let's take a look here. Notice that when I'm in my browser and I go to simply harvard.edu with no HTTPS, no : / no www, no trailing slash, enter, it all just sort of works and brings me to the intended place. Now, why is that? Well, at the lowest level, we can actually see this in our command line interface. Let me go back to my terminal window, which I've still full screened, and let me type this time curl -I, and then simply http : / harvard.edu. So I'm going to help the program a little bit and provide it with the protocol, but I'm not going to provide it with the secure version. I'm not even going to mention www. Let's see what comes back. Ideally, it's a 200 OK, because that's what means success. But what I see here is weirdly that harvard.edu has moved permanently. And this time, the status code, coming back from an older version of HTTP, in this case 1.1 instead of 2, apparently has a status code of 301. So it turns out that different types of responses indeed have different numbers associated with them. And 301 means moved permanently, a sort of redirection, if you will. And where is Harvard's new location? Well, if we scroll down among these headers, you'll see that, the server is additionally telling me that the location to which Harvard has moved permanently is https : / harvard.edu. Okay, so what this seems to indicate is that Harvard server really wants me to stay on the secure version of the website. All right, so let me go ahead and highlight and copy that. let me go ahead and do curl-i and that URL. So almost the same, except for the HTTPS this time and the trailing slash, and hit enter. But this time too, notice, and this time the server is using a newer version of the protocol. We're back to version 2. It's still telling me 301. It's not berating me by saying move permanently again, but 301 is enough for me, the browser, to know, oh, Harvard's website is now at this location, www.harvard.edu, again using HTTPS. And so, OK, let's do this one more time. Let me go ahead and copy that URL and do curl-i and that full URL. And now we're back to getting a 200 OK. So among the reasons that your browser is able to figure out what you want is because, one, the server might be telling it, no, go here. No, go here. OK, now you're in the right place. And frankly, browsers nowadays, in cooperation with servers that are configured in a certain way, will tolerate you typing in only harvard.edu and just know proactively, no. You don't want that. You want HTTPS and you want the www because the browser, for instance, has seen that response before from the server. But at the end of the day, it's really just these status codes that are enabling us to actually forge these responses. So we've seen a couple now. We've seen 200 for OK. We've seen 301 for move permanently. There's bunches of others as well, including, for instance, this one here. Odds are most everyone here has seen 404 at some point in their lives. I mean, it's sort of in the human vernacular. We all know that 404 means file not found. Like the URL is wrong, the file was deleted, something is missing. That's a little weird that we as humans have been acclimated to a fairly esoteric HTTP status code, but that's all it is. If you visit a web page that simply does not exist, you will get back not 200, not even 301. You'll get back a similar header like this saying 404, file not found. Now, you might see a web page, and it might be a cute web page, or it might be a black and white text-only web page. It depends how the web server has been configured to show you that information. But 404 indeed means file not found. And here's a non-exhaustive list of other status codes. We've seen 200 OK, 301 OK. There's other 300 level status codes that generally refer to redirecting the user from one URL to another. The 400s generally indicate user error, like your fault, my fault. So 401 is unauthorized. 403 is forbidden, like you haven't logged in properly. 404 is not found. 418 is actually an April Fool's joke from years ago. I'm a teapot was sort of a funny joke among engineers. More on that if you Google it if you'd like. 500 range errors means server error. So someone screwed up, maybe not you, but frankly, in a couple weeks' time, when you're writing web-based applications yourself, anytime you see a 500, it is your fault also. So you are both the user and the server in that there case. But long story short, the way these things work are simply underneath the hood via these status codes, which really are being sent virtually inside of envelopes like these. Your browser is generally hiding that detail because normal users don't need to care about this level of detail. But you've always had the power of opening your own browser's developer tools and poking around and seeing these things. And all I'm doing in my black and white window here with curl, which connects me to a URL using a command line interface, is showing you even more in detail what's inside of those envelopes. But it's just another way of viewing the same kind of information. Now, we can actually have a little bit of fun with this, with a smile and a wink to our students at Yale who are perhaps watching this now. It turns out, has anyone ever been to this URL here? safetyschool.org. I'll zoom in here in a new tab. Has anyone applied to safetyschool.org or visited safetyschool.org? Well, we love them equally. But turns out if you go to safetyschool.org, you end up at this here website, which if I zoom back in is apparently https://www.yale.edu. So what is going on there? Well, I could open my developer tools, but let me use my newfound command line skills and do it here. curl-i http://safetyschool.org, enter, and you'll see that, oh, safetyschool.org has moved permanently to Yale.edu's own website. So this is to a practical joke that has lived on the internet for years. There is someone out there, I don't know who they are, they have been paying an annual fee for years now simply to have this esoteric joke for us computer scientists. There are ones for Harvard as well, in all fairness, but this is one that's perhaps been around the longest. So somewhere there's a Harvard alum who's getting older and older, but is still paying this bill year over year since the web was invented.